Okay, question 11. We've got to calculate delta H for this reaction and then relate that to the enthalpy change of combustion. So the first job is that we're going to use a Hess's law cycle. Obviously you don't have to write it out properly because it's only a multiple choice question, but in essence this is how you're going to work it out. So remember that the data you've got are enthalpy changes of formation, and that's why I've written elements at the bottom, because as soon as you see enthalpy changes of formation you know that's what the link between the substances is. And formation means you take those elements and you turn them into the compounds. So those arrows represent the formation of the compounds from the elements. So the numbers it gives you, minus 723.8 for aluminium sulfide, but you've got two of them, so it's 2 times minus 723.8. The oxygen, well, that's still an element, so that hasn't changed, so no contribution from that, and that comes to minus 1447.6. Okay, so minus 1447.6 going that way. This one, going in this direction, we've got 2 moles of aluminium oxide, so that's minus 1675.7 times 2. And we've got 6 moles of SO2, so that's minus 296.8 times 6. And if you add all that lot together, you get minus 5132.2. if you go up to the right hand side. So then you invoke Hess's law, which says that that reaction across the top has the same delta H as if we do it in 2 steps like this. So starting here, coming down, and then back up again, ending up there. That has the same overall effect as this, so delta H will be the same. And you can see what delta H will therefore be, because the first leg of that journey is just the opposite of this one. So it's minus 1447.6 when you go that way, we're going the opposite way, so it's plus 1447.6. Second leg, we're doing exactly that, so it's the same number, same sign, minus 5132.2. And if you do that subtraction, you get minus 3684.6. But that's not quite the answer to the question yet, because the question said, what's the enthalpy change of combustion of aluminium sulfide? And remember, enthalpy change of combustion is when 1 mole of the compound burns in oxygen. So we are reacting with oxygen, which is right, but we're burning 2 moles of that. So you've got to halve that to get the enthalpy change of combustion. So if we divide that number by 2, we get whatever the answer is. I can't see it now. What is that? So we've got to divide that number by 2, and the answer is minus 1842.3, and therefore the correct answer was B for that one. Okay, so question 12 is making you think about what difference it makes to an experimental result if there's a problem during the experiment. So the scenario is that somebody's measured an enthalpy change of combustion for methanol, and the answers come out to be too exothermic, too negative, if you like, and the question is what could have caused that to happen. So you've got 4 possible explanations to think about. So the first one is, well, what if some of the methanol, rather than burning, actually evaporated? Which of these input parameters would that affect? And the answer is, well, it's going to affect this one, the moles reacted, because if some of it actually evaporated, all you would know is that the mass had gone down, and so you would actually think that it had burned, so you're overestimating how much burned, and that means this number on the bottom is too big, and if you divide by a number that's too big, you get an answer that's too small. In other words, delta H would come out not negative enough, rather than too negative, so that's not the answer. Second possibility says, well, what about when you're working out the moles reacted? What if you used the wrong MR? So remember, we're using moles is mass over MR. And if we used the MR for ethanol, which is a bigger molecule, again the MR on the bottom line would be bigger, so you're dividing by a bigger number, you get a smaller number of moles. Okay, so if the MR is too big, which is what it's suggesting, that means that the moles would be too small. And that means in turn that if we put this number on the bottom and we make it too small, that would give the right outcome, right? Because if this is too small, which is what we've now predicted, that would mean that delta H is too large, but because it's a negative number, we'd say delta H is too negative. So that one actually accounts for the result. So B is the correct answer for that. It's just worth quickly looking at C and D, even though we know that B was the right answer. If there was incomplete combustion, there would be less heat given out than expected. So delta T would be smaller than it should have been, and therefore Q would have been smaller, and therefore delta H would have been smaller or less negative. So again, that one didn't fit. And if the water had boiled, so if some of the heat given out was used to actually cause the water to boil, remember that requires heat inputs called the latent heat of evaporation, and that would mean that delta T would be smaller than it should have been because some of the heat was being used to do something else. So again, that would have made delta T too small, therefore Q too small, and therefore delta H not negative enough. So B is the only one that can give the right answer for that one. Okay, question 13 is all about Le Chatelier's principle, and the question is, what can we do to make this equilibrium shift to the right in favour of the products? So we've got two things to think about, pressure and temperature. For pressure, what Le Chatelier says is that whatever you do, it will try to do the opposite. So if you increase the pressure, it will try to decrease it, and it will do that by moving in the direction where there are fewer moles of gas. So these substances are all gases, and so you can see that on the left you've got 3 moles, but on the right you've only got 2. So if you increase the pressure, it will move in that direction to decrease the number of moles, and therefore decrease the pressure again and oppose the change. So increased pressure will cause it to shift to the right because there are fewer moles of gas. What about the temperature? Well, Le Chatelier says that if you increase the temperature, it will try to take some of that extra heat away and therefore decrease the temperature again, and so it will go in the endothermic direction. So we need to think, well, which direction is that? So we've got this number, remember, minus 197 relates to the forward reaction. When you have a reversible reaction, the value quoted for delta H refers to the forward reaction. So it's minus 197, which is exothermic going that way, therefore plus 197, which is endothermic going backwards. So if we want it to shift to the right, that's the exothermic direction, and that means we need to decrease the temperature, right? Because if you decrease the temperature, it will try to warm it up again by going in the exothermic direction, which gives out heat. So the answer is that decreased temperature will shift it to the right because that's the exothermic direction, and therefore that opposes the change. So that combination of things, increased pressure and decreased temperature, means that the right answer is C for that one. Okay, so question 14 is all about percentage yield, and this is the reaction. So the starting point is that we're told to get 500 grams of ammonia produced, so the first thing is we've got to turn that into moles. So we get moles as mass over MR is 500 over 17 for ammonia, which comes to 29.4 moles. And that's your actual yield. So remember, the definition of percentage yield is the actual moles you get divided by the theoretical moles that you should have got if the reaction had gone perfectly, times 100. And we're saying that the actual moles we got is 29.4. What we need to get is the theoretical moles, because the theoretical moles is going to be related to the moles of magnesium nitride, which is what we want. Okay, so the next job is to realise that that is 94%, because it's a 94% yield. So 29.4 is 94% of the theoretical yield, which means that the actual theoretical yield, which would be 100%, we've just got to scale up, so it's 100 over 94 times 29.4, which works out to be 31.3 moles. Okay, so it's important to convince yourself that you could do that step. Another way to approach it would be to rearrange this equation. You could do that and to make the actual moles the subject, to make the theoretical moles the subject, because that's what we want to know. So if you just rearrange that, you get that the theoretical moles is equal to the actual moles divided by the percentage yield times 100. And you can see that that gives us the equation we've got there, because the actual moles is 31.3, it's 29.4 times 100 divided by 94. So however you think about it, that's the calculation you need to do. So then you think, okay, well, how does that help me? Well, theoretically, each mole of magnesium nitride gives you 2 moles of ammonia. So that means that the moles of magnesium nitride is half of the theoretical moles of ammonia. So that's the next step, that we get moles of magnesium nitride is a half of the theoretical yield of ammonia. Because that's what the equation says, and that's what the theoretical yield is. It's what the equation says you should get. Okay, so that's half of the theoretical yield of ammonia, which is 15.6 moles. And the final step is just to turn that into a mass. So you get mass of Mg3N2 is moles times Mr, which is 15.6 times, if you add up magnesium nitride, it comes to 100.9, and that gives you 1580 grams once it's rounded a little bit, and therefore the answer is A for that one. Right, question 15, we've got these 4 compounds, we've got to work out which one of them needs 8 moles of oxygen gas for complete combustion. So we just work out what we're going to get. So for this one, we would get 4 CO2s, and 8 hydrogens means 4 waters, and that means a total of 4 2s 8 plus 4 is 12 oxygens on the right hand side, so we would need 6 O2. So that's no good, doesn't work. This one, got 4 carbons, so 4 CO2s. We've got 10 hydrogens altogether, 9 plus 1 is 10, so therefore 5 H2O. So that's 4 2s are 8, plus 5 is 13 oxygens. One of them is already there. You've got to be careful with these compounds that contain oxygen. So there were 13 oxygens altogether on the right. One of them's already there, so that means we need 12 more. So again, that's 6 O2. So that's no good. This one, 5 carbons, so 5 CO2s, 12 hydrogens, so 6 H2Os. So that's 5 2s are 10, plus 6 is 16. But again, one of them is already there, so only 15 extra oxygens are needed, which is therefore 7.5 O2. So that's no good. So hopefully it's going to be this one. So we've got 5 carbons and 6 waters. So 5 2s are 10 oxygens, plus 6 is 16. None of them are already there, so we need all 16, which is 8 O2. And therefore, finally, that one is the answer. So D for that question. Okay, question 16, we've got this molecular formula. It's got lots of structural isomers, but we've got to work out how many of those are tertiary alcohols. So we can do that by going systematically through using skeletal formulae. If you had a chain of 6, it's not possible to get a tertiary alcohol because you need to have a branch to make it tertiary. So that's not possible. But if you just have a chain of 5 and you put a branch in, you can put it there, or you can put it there. And if you put the OH at the branch point, so there or there, there, then those are both tertiary alcohols. So that's two possibilities so far, and those are the only two if we have a chain of 5 carbons. So the next thing is to think, well, what if we have a chain of 4 carbons? What are the possibilities? Well, if we put both branches there, then we can't make a tertiary alcohol because there's no room for the OH at that position. It's got to go here, but that would only be secondary. However, if we put the 2 branches like that, then we can make a tertiary alcohol by putting an OH on there. You might think, well, what about if we put it on this one? But you can hopefully see that those 2 compounds are the same thing, just rotated round, so that's not actually a different answer. And those are the only possibilities. If you only had a chain of 3, there isn't enough space to put all the branches in, so those are the only 3 possibilities. So the answer is 3, which is C. Okay, question 17 is quite a straightforward one. We just go through and count how many hydrogens there are there. So we just use the rule that in a stable molecule, a carbon is always going to have 4 bonds. So if we start here, say, that carbon has 3 bonds drawn, so it has 1 hydrogen on there. That one has 3 bonds, so it has 1. That carbon has 4 bonds, because double bond and 2 single bonds, so no hydrogens on there. This one has 3, this one has 3, this one has 3, this one has 3, and you can see just from the symmetry what's happening now, but it's just those 2 carbons which already have 4 bonds to other carbons, so they don't have hydrogens, but all the rest do. So you can see that you get 8 altogether, so it's C10, H8, and therefore the answer is A for that one. And question 18 again is a relatively straightforward one, because we're reacting pent-2ene with bromine. So that is pent-2ene, and if you react that with bromine, we know that all it does is add across the double bond. So what we'll get is Br there and there, and to name that, it's pentane now rather than pentene because the double bond is gone. We're going to start numbering the chain from that end because we've got to keep the first number as small as possible, so that way we get a 2. If we started from this end, it would be 1, 2, 3 before we got a number. So that's the correct order of numbering. And carbon 2 and carbon 3 each have a bromine. So it's 2, 3, because there are 2 of them. It's not just bromo, but dibromo. So 2, 3 dibromopentane is the answer, which is D, and therefore that's the correct one for question 18. Right, question 19, we've got to do the EZ thing for each of these double bonds. So if we look at double bond number 1, for this carbon, the methyl group outranks, remember there'd be a hydrogen here, but on atomic number, carbon outranks hydrogen, so that's the priority group at that end. At this end, they're both attached, both the attached atoms are carbon, so the directly attached atom doesn't tell you which one wins. But if you move one further atom away, this one only has hydrogens, but this one has another carbon. So it's that carbon 2 away that beats the hydrogen 2 away here. So that means that this is the priority group. So they are on opposite sides of that line. And if they're on opposite sides of the line, that means that one is E. Double bond 2 is more straightforward because in both cases you just have the carbon outranking the hydrogen. So this one is the priority group as far as this carbon is concerned, and this one is the priority group as far as that carbon is concerned. And again, relative to the line that runs through in the middle, again they're on opposite sides of that line, and therefore that one is also E. So EE is the correct configuration, which is C would be the correct option. Okay, the last question then in question 1, you've got to figure out which of these could give you a mass spec fragment with an M/Z of 31. These structural formulae, all in one line formulae, are horrible, and it's very easy to make mistakes with them. So what I would probably do is just very quickly redraw them as skeletal formulae. You don't have to do that, but it's what I always tend to do because I just don't really like them. So you just think, right, that's got a chain of 4 carbons, and that third one has an OH attached, because that's what the OH in brackets means. So that's that compound. This one, you've got a chain of 3, 1, 2, 3, and then the 4th carbon, which is this one, has an OH and 2 methyl groups attached to it. So there's your 4th carbon, and it has an OH, and it has 2 methyl groups attached to it. So it's that is your compound. This one, CH3, then the second carbon has the OH branching off it, and then CH2, CH2, CH3. So it's that one. And finally this one, this carbon has 2 methyl groups attached. So we've got the 2 methyl groups attached to this carbon here, and then there's CH2OH. So those are your compounds. And we're saying if you break them, can you get 31? It pays you in the end, if you do enough mass spec examples, to learn to recognize certain masses. So for example, CH3 plus, you know, is going to be 15, okay, 12 plus 3. If you have an ethyl group, you get 15 plus 14 is 29. So things like that are quite helpful, because you immediately know, for example, that if this one breaks here, that end is going to be 29, so that's not going to give you a 31 peak. You can also see that this one is going to have 2 carbons and an oxygen, so that's going to be too big. You can't get it from that one, so that's no good. So the question is there a 31 fragment that you might know in advance? And we'll see once we've worked it out that it's one that actually you could have done this question a lot more quickly had you known. But we'll just go through. You can see if you break this one, methyl's too small. If we break it here, we get 29 again. That's no good. If we break it here, we can get 15 or 15 or 17. If you break it there, that's far too big, so nothing doing there. Here, you can break methyl off, which is too small. You can break something too big off here, which adds up to much more than 31. And if you break it here, you break 29 off. So again, you can't get 31. But this is the one where you can, because if you break it here, you get CH2OH plus. And if you add that up, you get 14 plus 16 plus 1 is 31. So that's the one that can do it. And you can see any primary alcohol is going to have that CH2OH plus as a possible fragment. So it's just worth doing lots of mass spec practice, so that come the exam you just sort of recognise that and you think, oh yeah, that's probably going to be CH2OH plus. But in the end, as you can see, you can work it out systematically. So that's the only one where if you break it there, you can get a 31 fragment. So therefore, D was the correct answer.